In the vast, silent theater of the cosmos, stars are born, they shine, and they die. But every so often, the universe stages an ending so colossal, it defies comprehension. On a quiet day in 2018, a flicker of light reached Earth. It was faint, almost unremarkable, but to the European Space Agency's Gaia spacecraft, it was more than a blip. It was the first sign of the most powerful explosion since the Big Bang. Gaia was designed to map our Milky Way in unprecedented detail, measuring the positions and brightness of over 1 billion stars. But it also had a secret talent, watching for transients, sudden changes in light. On September 9, 2018, Gaia detected an unusual optical flare. An outburst now designated as Gaia18cdj. At first, scientists thought it was a typical supernova, a dying star's final scream. But something wasn't right. At first glance, Gaia18cdj resembled something familiar, a brilliant flash in the darkness. A hallmark of a supernova, the explosive death of a star, but as scientists dug deeper, the light refused to behave. Supernovae are common cosmic events for a universe. When massive stars run out of fuel, they collapse under their own gravity and rebound in a violent outburst, ejecting outer layers and leaving behind neutron stars or black holes. These explosions are incredibly bright, but also brief. Typical supernovae rise to peak brightness within a few days to weeks, then fade over weeks to months. But Gaia18cdj refused to fade. Instead of dimming, Gaia18cdj's light continued to grow, reaching its peak over 200 days after it was first detected. And once it peaked, it remained astonishingly stable, radiating enormous amounts of energy for over 3 years. Supernovae don't behave this way. Next, the scientists came up with spectroscopy, splitting the light into its chemical components. Supernovae have distinct signatures depending on the elements in the star: iron, silicon, hydrogen. Gaia18cdj lacked many of these. Instead, its spectrum revealed persistent high-energy emissions and characteristics consistent with material orbiting and falling into a black hole. Then came the final surprise, its total energy output. Gaia18cdj radiated over 25 times more energy than SN 2016 APS, which, until then, held the record as the brightest known supernova. In just 1 year, it released more energy than 100 suns will generate over their entire 10 billion year lifetimes. Astronomers realized Gaia18cdj belonged to a newly recognized cosmic class, extreme nuclear transients, or ENTs. These are not quick flares. These are drawn-out, catastrophic feasts, where black holes hundreds of millions of times the sun's mass consume stars several times more massive than our own. Unlike typical tidal disruption events, ENTs glow smoothly, for years. Their energy output is monstrous. Gaia18cdj released in 1 year more energy than 100 suns would produce over 10 billion years. Gaia18cdj has rewritten the rules of cosmic violence. It proved that supermassive black holes can eat massive stars in long-duration episodes, not just quick, one-time meals. It also offered a new tool to probe the extreme physics near black holes, magnetic fields, relativistic jets, and the very structure of galactic nuclei. And because Gaia18cdj was so bright, it could be seen across billions of light-years, letting scientists peer into the distant past, into the era when galaxies were forming and black holes were growing most rapidly, a period known as cosmic noon. Thanks to Gaia and new observatories like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory, we are entering an era where the skies are scanned nightly, with machine precision. Events like Gaia18cdj will no longer be rare surprises. They'll become part of our new cosmic language. Gaia18cdj reminds us, the universe is not quiet. It is alive with colossal deaths, and new beginnings. Every flicker in the sky may be the echo of a star caught in a final, magnificent fall into darkness.